Hello, YouTube. There's a cat in my room being a little bit difficult, but should be fine. Today we're going to be doing some harder problems for hills and systems. Actually, the same problem that is harder for both hills and systems, as well as doing a problem that's a little bit harder because it looks like a system but isn't. I'm going to talk a little bit slower because that's kind of a good thing to do, but also because I know that most of the time the people watching this video watch it on double speed. So, that's fine. Ideally, end of the day, you should be able to model the motion. Oh, I forgot to change this. That's fine. So, we've got this problem. So the reason that this problem is tricky is that you've got to use both hills and systems. But if you're familiar with both of those two separately, it's actually honestly not that bad. The next one that we're going to deal with is actually going to involve some algebra because we can't just set up a system of equations using systems. We have to set up a system of equations the old-fashioned way by thinking about the relationships between how the two objects move. So, doing our first one. This cat is doing things. So for our first one, we've got our hill, we've got M1, which is 5 kilos, comes up here, it makes a pulley, and then comes down to this one. We've got an 80-degree angle, we've got a 40-degree angle, and that means that this is going to be a 60-degree angle? Is that right? Over by 20, under by 20? Yeah. To add up to 180. Oh, I swear. I'm probably going to have to kick a cat out in a sec. And this is M2. Yeah, they're going to knock stuff off the table. All right, cool. So, that's all our info. Let's hop to it. So, diving on in. Well, looking at M1, we're going to use our rotated reference frame. Doing that, gravity's going off at this angle. We've got our component of gravity going into the hill, and our component of gravity going down the hill. I just used different colors in the other one. I should try to keep it consistent. Great. So we've got mg cosine theta going down the hill, and mg sine theta going into the hill. And these are both going to be theta 1. Great. Then we'll have some normal force going up the hill, and some tension going up the hill as well. Sorry, normal force going perpendicular to the hill. For object 2, because we should definitely draw out a second free body diagram for our second object. There's like a guitar pick or something under here. Oh, well. Maybe I can get it. Not easily. There it is. Welcome. For our second object, we've got our hill, we've got our dot, and we've got our normal force. This should be normal force 1. We've got our M2G 1 with its own components. And we've also got the force of tension going to the left on this one. And so, boop, boop, and boop, boop. This is mg. Oh, sorry. This should be sine. This should be cosine. Just spent the long video, by which I mean 10-minute video, talking about that. And this one should be mg cosine theta, and this one should be mg sine theta 2, theta 2. So, we've got this thing going along the hill, we've got this thing going into the hill. Great. next step for all of these is pretty much going to be to identify which of these we want to call forward and which of these we want to call backwards. Now, because we've rotated both of these reference frames differently, we actually do have to be a little bit careful about this. But because the way I've rotated them, we don't have to be that careful. For this one, I'm going to call up the hill forward. That pen is still not happy with me. And for this one, I'm going to call down the hill forward. So when I do that, what I can do is, in setting up my equations and sort of making a super conglomerate free body diagram, we'll have the force of tension going backwards. We'll have the force of tension going forwards. It's the same rope, and we're not caring about the mass of the pulley. So those two will cancel out. This is nice because what that leaves us with, I'm just actually going to redraw it because, again, those cancel out, is mg sine theta 2 going forward and mg sine theta 1 going backwards. Give myself a little bit more room to work with. Great. And mg sine theta 1 going backwards. I don't have to worry about mg cosine theta because that's going to cancel out with our normal force, and I can actually just show that here. So we've got Fn2 and mg cosine theta 2, Fn1 and mg sine theta 1. These two should be smaller than these two because actually it depends on the angle. But in any case, the two on either side are the same as each other, so we don't have to worry about them for our super system. So our net force in our y direction, 0. Our net force in our x direction, more useful for what we're doing here. So all we have to do to figure out our acceleration in our x direction is say that mg sine theta 2 minus sorry, I should be careful about that. m2 sine theta 2 minus m1 sine theta 1 needs to equal their combined mass times their acceleration. Because this is for our system of 1 plus 2, so we have to use our combined mass at the end. So again, going over that process, I did a free body diagram for each separately just to make sure I knew what was happening because this one's a little more complicated. I thought about which of those forces were pulling them forward and which of them were pulling them backwards. The ones pulling them forward were mg sine theta 2. The ones pulling them backwards were mg sine theta 1. Everything else cancels out. That leaves me with just this equation where those are my only two forces that I'm using, and that will need to equal ma, but because it's a system, it'll be their combined mass times the acceleration. Great. So, what I can do now is divide each side by their combined mass. And when I do that, I've got an acceleration. The reason this matters is we'll get m2 sine theta 2. I'm going to factor out the g because they both have g in common. Minus m1 sine theta 1 times g divided by m1 plus m2. And that'll just give us acceleration. Putting in our numbers, we've got 10, we've got sine 60 minus 5 sine 40. And that's being divided by 15, or 5 plus 10. I should bother finding my calculator now. Or, hear me out on this one, I can just use the calculator that is Google. And I need to be in degrees. So we've got 10, parentheses, 10 times the sine of 60 minus 5 sine of 30 divided by their combined... Oh, nope, not 30. 40 divided by their combined mass of 15, which gives me a very small number indeed. For some reason I thought it'd be bigger. Okay. Yeah. Huh. 10 degrees. Okay. In calculator we trust. 0.36 meters per second squared. Now this isn't our answer, right? We're asked to find the tension. But the reason I found this first is because rather than having to set up two equations and do a system of equations that's more complicated up here, what I can do is I can use this acceleration and then look at something like system 1. In the x direction for system 1, we've got force of tension going forward, mg sine theta 1 going backwards, and that needs to equal to mass times the acceleration of the object, which should be forward. And at this point, my only variable here is ft. So if I take this and add mg sine theta 1 to both sides, I'm done. And this way I don't have to worry about which ones are plus and which ones are minus when I'm doing my system, which can sometimes get pretty cumbersome. And instead, we'll just wind up with mg sine theta 1 plus m1 times our acceleration, which is 5 times 10. Oh, I forgot g. That'll do it. I was going to say that seems small. Fixed it. We're good. 3.6. Times sine of... down here. So between this line and this line, where I actually put in the numbers, I originally hadn't included the g, so I got 3.36 instead of 3.6. Just needed to multiply by 10. This is sine of our 40-degree angle plus 5 times 3.6. So 50 sine 40 plus 3.6 times 5 is... Whoa, whoops. Forgot to close my parentheses on the sine function. There we go. Just about 50 newtons. So this is our force of tension. And we should get the same if we do that for the other one. So that's our first one. Our second one, it's getting a little bit later than I'd like to be doing these normally, is a little trickier. Oops. In that we'll have to actually do some algebra. So we've got a cart that is being dragged by a pulley system. In particular, we're trying to find the acceleration of the cart. We're going to ignore friction for this one, say it's on wheels. And this one's again a little bit of a false, not again, this one's a little bit of a false system, in that they don't actually move together, and we'll talk about why. So we've got our cart, nice, which is 10 kilos. That's M1, which is flipped from last time, but should be fine. We've got our hanging mass, which is 5 kilos. And we've got 2 ropes coming out of our hanging mass. Now, the reason this matters is because if you take a length of rope and you feed it through here. Eventually, it's going to have to bend around this rope. And when it does that, half of the rope that you fed down here will be on the left, and half of the rope will be on the right. And so what that means is that the distance traveled by the first one is going to be double the distance traveled by the second one. And if we take a second derivative of that, that means that our acceleration will also be double. So a1 is actually equal to, and if we're being really careful about it, a1x is equal to negative double a2y. Because any negative y acceleration experienced by the second mass is going to lead to positive acceleration by the first one because it's going to the right and this one's going down, if we're qualifying right as positive and down as negative. That makes it kind of annoying to set up a system unless we're using a system of equations, because we can't just say that they're traveling together, so we can't pretend that they're exactly one object. What we can do, however, is the slow and steady on actually setting up a system of equations. So doing that out, we can do that for mass 1. Our free body diagram should look like normal force going up, gravity going down, and the force of tension going to the right, m1g. Great. For mass 2, we can set up, there we go. For mass 2, we can set up that we'll have 2 ropes pulling up, each of them with the force of tension. Additionally, we'll have m2g pulling down. And so when we're trying to figure out our accelerations, we have to be careful with a1 and a2. The x direction is the direction that it's actually moving for m1, so that's the one that I'm going to care about. We've just got the force of tension, and that needs to equal m1 times ax. In the y direction, for object 2, we'll have because that's the direction it's accelerating, we'll have 2 forces of tension going up, so 2 times ft, minus m2 times g, and that will need to equal m2 times the acceleration for block 2, and I should be careful for this is for block 1. What I can now do is use my earlier bit of logic about the ropes feeding and doubling. Again, the big thing is that whatever rope comes through here needs to pass along that pulley. When it does, it'll bend. And by the time that half of it is here, half of it will be over here. And so that means that any distance traveled by this one, which has to feed all the way through in a straight line, gets bent back in half before it actually gets the rope to go down by, well, only half the same amount. Will give us that a1x is equal to negative 2a2y. So what I can do here is substitute this one for, and I'm going to ignore the positive and negative the way I've set it up. Nope, the way I've set it up, down is negative. So I do have to actually be careful about that. Negative 2 a2y. I am trying to solve for the acceleration of the cart, actually, so I'm going to go ahead and really quickly divide by negative 2. And the reason I'm doing that is just so that the variable I get here is the cart, not the other one. So this should be subbed with negative 1/2 a1x, because again, looking for the cart, so I want to use the acceleration of the cart, so I don't have to bother plugging it back in at the end to find the acceleration of the cart, because I accidentally found the acceleration of the block. Thankfully, what are our variables here? We don't know the force of tension, we know the mass, we don't know the acceleration. We don't know the force of tension, we know the mass, we don't know the acceleration. Only variables here are tension and acceleration once we've made that substitution, so we don't have 2 different accelerations. That part's important. This is nice because this one's already solved. So I can take this force of tension and replace it with just max. And when we do that, what we'll wind up with is 2 times m1 and I'm just going to call it a1 minus our original part of the equation of m2g needs to equal m2 times, and doing this substitution, careful, this is negative 1/2 a1. Great. We're now trying to solve for a1. So we need to get every term without an a1 on it to the same side as each other, and every term with an a1 in it to the same side. I'm actually going to subtract off 2ma1. You could do it the other way around, but this will just save me a little bit more algebra later down the line. That gives me negative m2g is equal to negative 1/2 m2 a1 minus 2 m1 a1. Really quickly before I go any further, all of these are negative, so I'm just going to swap them all to being positive by multiplying each side by -1 or dividing it by -1, dealer's choice. And now we can substitute out a1, and once we factored out a1, and once we've done that, we'll wind up with m2g is equal to a1 times 1/2 m2 plus 2 times m1. So then we just have to divide each side by our common variable. And we're left with our answer that our acceleration will be m2g, the force that's accelerating it, scaled by some weird relationships between how the scaling factors work with the two masses. In this case, we'll get 5 times 10 divided by 5, 1/2 of 10, plus 2 times 5, so 10. So 50 over 15, which is 10 over 3 meters per second squared. Woof. That's how you do that one. So not too bad. Honestly, 20 minutes for 2 problems is pretty good, but certainly a little more involved than if you didn't have a combination of hills and systems, and certainly a little more involved than if you could just use normal systems of equations to solve it, because you do actually have to do some minor amount of substitution, and you have to do some thinking along the lines of keeping track of and being careful about how their accelerations are related to each other. In particular, mistake I almost made, messing up the signs on the relationship between those two accelerations based on me having defined down as being negative here. Great. Well, that's it. So goodbye, YouTube.